the slides, I had some other things in mind. So one thing that I was trying to understand, one thing behind this was trying to understand integration of differential graded algebras. So there are some different ways of integrating differential graded algebras. I mean, there are these papers of Getzler and Enriquez about integrating DGAs. About integrating L-infinity algebras, in particular differential graded algebras. But things are more about cohomologically graded DGLAs. So I was okay. So let me say what I was exactly trying to think about. So if you have a Lie group G, you can associate to its Lie algebra G. So Lie group, Lie algebra, and there is another source of Lie algebras, and this is discrete groups from. So if G is a discrete group, well, we can associate to it the Lie algebra, which is the direct sum of the successive quotients of the lower central series of G. And this is going to be a Lie algebra as well. Now, here we have Lie's theorem that allows us to reconstruct the Lie group from the Lie algebra, at least in finite dimensional case, and say up to covering. Here we don't have the same thing. I mean, a better way of doing this would be via Maltsev completion, and then, well, if you do it via do this thing via Maltsev completion, it's clear where the information is lost when you get from here to here. But anyway, this construction that associates to a discrete group the corresponding Lie algebra is, well, it's the basis of linear methods in the combinatorial groups here. So when you have some kind of object which is like a Lie algebra, and you want to integrate it, it's a good idea to, if your construction, apart from producing a Lie group from a Lie algebra, would have some sort of a discrete version of an integrating object, giving you some sort of a tangent object in a combinatorial way. So if so integration is really not a very difficult thing. I mean, you have at least formally. So if you have, for instance, a formal product on a vector space. So a formal product on a vector space is nothing but a map of a symmetric algebra of V plus V to V. This is really can be deciphered in the following way. So this is you have a coordinate x here, a coordinate y here, and the elements of the symmetric algebra are polynomials. So this thing is spanned by the monomials too, and to each monomial you can associate its coefficients here in the same vector space. So a formal multiplication consists, I mean, if V is finite dimensional, then a formal multiplication consists of several power series Fi in x and y, and these Fi are the coordinates here. So this way we get a map of this kind. So this is the formal product. So from this kind of formal multiplication, I mean, so far I'm talking just about any formal multiplication on a finite dimensional vector space, not necessarily associated. So from here you can lift this thing to a co-algebra morphism, and so this is going to be an algebra. And so if we start with a formal Lie group, so this thing is going to be the universal enveloping algebra. Of the corresponding Lie algebra. So this is an algebra. It's actually a Hopf algebra. There is a co-product here, and on the symmetric algebra. So you take the primitive elements, and so you take the primitive elements, and you get the Lie algebra. So integration is taking, well, in many contexts, the formal integration is just going backwards. You take your tangent structure, it's a Lie algebra or whatever unknown Lie algebra you may have. You take its universal enveloping algebra in whatever category you're working, and then you just project this algebra map onto this onto V, onto the space of primitive elements. So this is how integration works, and in a sense, if in many contexts, really formal integration is not a problem at all. So the real problem is finding an integration that has some geometric meaning. And so there's so the problem of integrating differential graded Lie algebras, say homologically graded. Well, from the formal point of view, it's not really a problem. You just do it. You get some kind of formal product. But the question is, of course, what is the meaning of this product? The question is for instance, I mean, do you have some kind of a discrete like group-like object that, as its lowest central series, would produce some a DGLA? It's okay. So it's a kind of a. It might sound like an, but there was a much simpler question that was mulled for many years. People tried to integrate Leibniz algebras, and so the Leibniz algebras are basically one-dimensional germs of homologically graded DGLAs, and integrating them should be very easy via this way. I mean, you can do it. The question is, what is the geometric meaning? And somehow somehow people have arrived to a solution, and the solution is RACs. Now, RACs, I don't know. I mean, I don't know how. I mean, it's the concept of a RAC is a very useful thing in some subjects, like for instance in knot theory. But I think I'll have to say a few words about what these things are. And so what I will talk about is how to, I mean, in the end, one can look at this story as some kind of a partial integration of DGLAs, like in degrees 0 and 1. It's not, well, you'll see. So the good thing about it is that we have some discrete objects that give us some kind of associated tangent structures, and these are going to be linear algebras in the category of differential graded vector spaces up to terms of degree 2 and higher. So I have a feeling that this was not a very good introduction, but this is going to, I mean, the slides are going to be more clear than this. So first of all, what are these racks? The word is unfortunate, and that's why they're probably not very popular. I mean, the terminology was invented by Conway, and Conway wrote them with W, racks, and so they had no furniture associated meanings, this term. So a rack is basically what you get if you axiomatize the conjugation in a group. So right, so we have an operation, x to the y, and this operation should be secretly thought of as something like this. And the conjugation satisfies this self-distributivity identity. So a rack is simply a set with a binary operation which satisfies this self-distributivity identity, which is so characteristic for the group conjugation. Also, there is another condition, is that basically the conjugation is something invertible. And racks, really, I mean, a rack is a non-associative structure. It looks somewhat exotic, and it has a very clear associative interpretation. So an augmented rack is simply the same thing as a crossed G set. You have a set with an action of a group G, and you have a morphism of this action into the conjugation of G on itself. So if you have an augmented rack X, then you have a structure of a usual rack on X. So we take how do we conjugate one element with the other? We just project one of these elements into G, and then sort of conjugate with this G. This is the idea. So if you have an augmented rack, then X is canonically a rack, and on the other hand, if you have a rack, you can define an associated group. You can define many associated groups. You can associate many groups with a rack, but there is one canonical group which is called the associated group, and basically we try to imagine that a rack is a conjugation rack of a group, and we try to reconstruct this group. So this is what we get. This Gx is what the rack X would look like if it were a group. So the associated group is just defined by a presentation. Now, actually, people For some reason, racks were they used just racks, not augmented racks. I mean, there are some. So, for instance, there's one thing which is another motivation for this talk that I didn't mention. There is a homology theory for racks, and well, it's valid for racks, not augmented racks. Rack homology. You don't really need to know much about this group. So, okay, so the first example, of course, are the conjugacy classes in a group. Then the second example is quite good, but nobody ever uses it as an example of racks because well, you don't really need it somehow. You don't need to consider a root system as a rack. Well, how does it work? So the Weyl group acts on X, obviously. So, and each root projects into the corresponding reflection. So it's an augmented rack by definition. Now, why nobody thinks of root systems as augmented racks? Well, there is one interesting invariant of racks, and this is rack homology, as I said. And it turns out that for all finite racks, this rack homology doesn't really detect anything. So if you, the only thing that rack homology would detect in a root system is the number of elements. So this is not very interesting from the rack point of view. This is a good example of an augmented rack, and really this is more or less how the integration of Leibniz algebras work. I will probably say a little bit more about this later. So this is the useful example. So let me show you how it works. So a more usual example of, well, probably the most famous example of a knot invariant is the group of a knot. Just the fundamental group of the complement of a knot in R3. And there is another invariant, which is the fundamental rack of a knot, and it works in a very similar way. So we have a base point outside the knot, and we have a path which runs around in the exterior of the knot, but this path is not a loop. It doesn't go back to the base point. It just ends on the knot. And for this construction really to work, we need the knot to have a kind of a thin parallel around it. We want to know a direction from which one has to come to the knot. I mean, these kind of knots are called framed knots. It's really the same thing as knots. To give a framed knot is the same thing as to give a knot together with a number, which is the linking number of this second copy of the knot. So this is an element that represents, so this path represents an element in the fundamental rack of the knot. And we consider these paths up to homotopy, as if it was the fundamental group construction. And of course, this endpoint can be moved along the knot. This one is fixed, and this one is movable. So so the homotopy classes of these paths, they're the elements of the fundamental rack of the knot. So what's the operation? Well, in order to define an augmented rack, first of all, we want to project each element of the rack to the corresponding element of the fundamental group. So we start here at this base point, we go around this path, but then instead of hitting the knot, we just go around it once, and then go back along the same path. So this is this is the element of the fundamental group that corresponds to the element of the rack, and this is an attempt to represent the rack operation. So if you have this path and this path, so this path acts on this one by just precomposing it. So first we go around this path, around the knot, we come back, and then we go along this path. So it's just a composition in a way. I mean, so if you have any element of the fundamental group, we can go around this element, this loop, and then go along this path which ends at the knot. This way, the fundamental group acts on the rack, just precomposing these paths with loops. So, to tell the truth, it looks like a silly construction. I mean, it's not clear why it's of any use. But there is a very concrete answer to that. The fundamental group is a very good invariant in the sense that it distinguishes prime knots. But it's very difficult to prove that this is actually the case. So it's a very difficult theorem that fundamental group distinguishes prime knots. In contrast, the fundamental rack of a knot is quite easy to show that knots with isomorphic fundamental racks are isotopic. The racks, somehow it's the same thing as considering a fundamental rack is more or less the same thing as considering the fundamental group of the knots together with a peripheral system, if you know what it is. So it's much more information, and it's enough to reconstruct the knot. Also, in the same way as you can write down the presentation for the fundamental group of the knot, you can write down some sort of a presentation for the fundamental rack. So it's a very calculable invariant. That's why it's so good, and it's actually useful in knot theory. But then, again, I mean, this is only an example. Right. So the whole proposition of today is that there is some kind of good objects that should be considered, and these are multiplicative graphs. And these multiplicative graphs have something to do with Leibniz algebras, and more generally with DGLAs in dimensions 0 and 1. So a graph here, for me, is really, it's not quite what graph theorists call a graph. It's just a set of vertices, the set of arrows, and we know where the arrows start and where they finish. So it's just two sets with a source and target maps. And in graph theory, people talk about the Cartesian product of two graphs. And the Cartesian product of two graphs is something like this. If you have, I mean, just one example basically explains it all. If you have this graph, the Cartesian square of this graph is going to be a square of this kind. So it's the true Cartesian square of this, it's the true Cartesian product on the set of vertices, and then we just replicate the first graph along one direction and the second graph along the other direction. This is basically what this thing says. Another way, probably a more understandable way, is if you think graphs as some sort of cubical complexes. You take a product of these two cubical complexes and just erase the cells of degree 2. So it's the usual Cartesian product, and then we just forget about the degree 2. Now, it really is, this Cartesian product is not a categorical product. It's not a product in the category of graphs, at least with the usual morphisms. I mean, there is a way to tweak this whole thing so that it becomes a categorical product, but it doesn't really matter for us. So the only thing that matters for us is that the Cartesian product is associative. So let's call a graph Cartesian multiplicative in some very naive way if it comes with some sort of multiplication, which is a graph morphism from the Cartesian square of Q to Q. And, I mean, the associativity makes sense here. And absolutely automatically, the vertices of such a multiplicative graph are going to form a semigroup. And, well, the semigroup-like graphs, I mean, are interesting. There are interesting, good examples. But let us consider only those graphs so that this multiplication on the set of vertices gives us a group product. So what kind of things are those? So this, again, this basically shows that there is nothing strange in the definition of a group-like graph. So we have a group structure on the set of vertices, and we have a two-sided action of the group of vertices on the set of edges, which is consistent with the source and the target maps. And the left hand, the associativity implies that these actions, the left-right action commute the right action. Okay, so really group-like graphs are the same thing as augmented racks. It's the same category. It's the same category, but in a much nicer packaging. That's the whole point. So if you have a group-like graph, we can consider the set of arrows that emanate from the neutral element of the group. So we take the identity in the group, and we consider all the arrows that start there. Well, there can be loops as well. So if since we have the two-sided action, we can act on the left by G inverse and on the right by G. And since this action is compatible with the source and target maps, it doesn't move the beginning of the arrow. It doesn't move the source. So we have the action of G on we have the action of the group of vertices on the set of arrows. And this action is compatible with the target map. So, I mean, I don't have anything to draw. And this way we get an augmented rack. And conversely, if we have an augmented rack, it's quite straightforward to construct the corresponding multiplicative graph. So far, this means that we really didn't do anything new, seemingly. However, it's really much more useful to consider multiplicative objects than self-distributive objects. Racks are self-distributive, and for some people it's some kind of nice exotic touch that this product is not associative. But it's much less intuitive then, however. If we, however, the multiplicative graphs are really much more natural. So this is an example. It's not a very useful example, but it's an example. There are many similar examples. So if we take geodesics on a Lie group, then the Lie group itself acts on the geodesics on the right and on the left. And I mean by geodesics, I mean intervals of the geodesics. An interesting thing about this example, about these geodesics parameterized by length, is that the fibers of both maps from the set of all geodesics to the group G are vector bundles, are vector spaces. So we're talking about two vector bundles here. This is really a funny graph. I mean, we shouldn't really talk about it as a graph. It has more structure. But this is one example which is useful for the integration. When we talk about the racks that correspond to nodes, this also gives you a somewhat nicer construction. So the vertices of the graph that corresponds to a node, they're just elements of the fundamental group, right? The vertices should form a group. This is reasonable. And an arrow from this element to this element consists just of one crossing. So instead of paths that start at some point and finish on the node, we just have some sort of transformations as the arrows. We just cross the node once. And again, this is one reason why very similar things have appeared in the theory of finite type invariance. And finite type invariance, well, it's slightly different. People study singular nodes when nodes have crossings. Here we have crossings of a path in the exterior of the node with the node itself. But it's a whole subject for discussion. I mean, how these things work. And this is the universal example of a multiplicative graph. So this is really where these graded, the differential graded subject appears. So cubical complex. A cubical complex, it's a pre-cubical set. I mean, when you speak about cubical sets, you speak about this, the sets that have two kinds of maps, degenerations and faces. So for simplicial sets and for cubical sets, these degenerations are necessary for defining correctly the product, right? We want the product of two cubes of the same dimension to be again the cube of this dimension. But precubical sets, they don't have degenerations, so the only product that you have is that an I-dimensional cube by an J-dimensional cube is an I plus J-dimensional cube. So if you have a precubical set with a multiplication on it, with an associative multiplication, then, well, it's immediate that the one-dimensional skeleton of such a set is a multiplicative graph, because we multiply the one-dimensional cubes by zero-dimensional cubes, and we get one-dimensional cubes again. So this also works in the simplicial setting, but I'm really into cubes here for some reason. And this reason is the following. So if you have a multiplicative graph, you can actually reconstruct some sort of a universal pre-cubical set with a multiplication on it. And this cubical multiplication is really, well, it's really something easy. I mean, at least something easy to define. Well, it's actually easy to describe as well. So one way to do it is to consider, so we consider our multiplicative graph as really as a topological space, as a graph, and we take the free group generated by of this graph. I mean, it has a huge number of generators, right? It's a very big free group. It's what's called the James reduced product of this graph Q. And, well, I'm lying slightly. I mean, I don't want to take the free group. I want to take the free monoid. It doesn't really matter for the James construction. I'd prefer to be precise here. So if you take a topological space X, and then you take the free group generated by all the points of X, and, well, this X is supposed to have a base point, and this base point is going to be the neutral element of this free group. So James identified of this free group, free monoid or free group, they're homotopy equivalent, so it doesn't matter. So the homotopy type of this free monoid is going to be the loop space, the based loop space on the suspension of X. So for instance, if you take a circle and you take the free group generated by the circle, or the free monoid generated by the circle, you get the loop space of the two-dimensional sphere. And this is already a trivial space, right? So this construction, this James construction, the construction of the free monoid on a graph, for instance, it gives you a combinatorial decomposition of this f of this graph, because, well, you can take cubical. I mean, this thing has a natural cubical structure. For instance, if x1 runs here, x2 runs here, the product x1 x2 will run over here. You'll have one cell which is the product of this one with this one. And this is why James construction is useful. It gives you an explicit cell decomposition of loop spaces. That's why it's used in topology. So here, well, you don't have a circle. You have I mean, any graph is topologically is a wedge of circles. But really, I'm not going to use this at all. All I want to say here is that we have this free monoid, and we can introduce a couple of equivalence relations here, which is that multiplying a vertex by a point on an edge, multiplying it in this free monoid, should be the same thing as the left action of this vertex on this point, and the same thing with the right action. So this way we get some cubical set. I mean, this cubical set, it's not just a set; it's a product. I mean, it's a quotient of a monoid by some relations, multiplication on a cubical on a cubical set. For any multiplicative graph. So again, multiplicative graphs, they can be thought of as racks. So with each rack we associate a space with a cubical space with a product. And these cubical spaces with products are not exactly completely unknown. I mean, what happens is that the group of lattices acts on this cubical space. I mean, in the end, you can think of the points of this cubical space as what? As sequences of elements, sequences of points on this graph. So multiplying a sequence on the left, we multiply just all of these points on the left. What we have really is a free action of the group G on this cubical space. So if this graph or multiplicative graph is called Q, we associate EQ with it, which is this cubical product, and then EQ mod G is something we can call BQ. And this is a known construction. It's called the rack space. And the homology of this rack space, or the cohomology of this rack space, is known as the rack cohomology. Now, somehow, people who study rack homology and cohomology, they proved some properties of this rack homology, which don't seem to be obvious at all from if you don't know that there is a product above this space. So, for instance, it's known that this space, the action of the fundamental group of this space on the homotopy groups is trivial, and this is a very, I mean, this is obvious from the fact that EQ has a product, but in principle, it's not clear why this is the case. So this is one use, for instance, of this kind of construction. So let me now go to a slightly different direction. So this is something that I mentioned. So this Ladei-Pirashvili category of linear maps, it appeared in a paper by Ladei and Pirashvili, where they were trying to interpret Leibniz algebras as some kind of mainstream objects. So the objects in this category are just linear maps between vector spaces, and it has something that Ladei and Pirashvili call the infinitesimal tensor product. And it's quite similar to the Cartesian product of graphs. So in degree 0, it's just the usual tensor product, and in degree 1, it's this kind of crossed construction. I don't know why they didn't really notice that this is just the tensor products of two chain complexes. So you take two chain complexes. If you consider chain complexes modular terms of degree 2 and higher, then this is the category of chain, say one-dimensional germs of chain complexes. That's what it is. Now, I guess there is there is a certain temptation, instead of considering Lie algebras in this category, what people do is consider GLAs which are 0 in degrees above 1. But this is a completely different object. Something like Lie 2 algebras. It's something quite different from this one. Well, anyway, so this is the Ladei-Pirashvili category, and you can define algebras in this category, and of course you can just say that it's a piece of a differential graded algebra, but you can define this by hand. I mean, and so this is here I'm trying to explain what a B algebra is. So this is a coproduct in a B algebra in Ladei-Pirashvili category, delta 1, delta 0. Well, delta 0 is the usual coproduct, and delta 1 is something like this. And delta 1 and delta 0 are related by this identity. Now, also there is a notion of an antipode. Well, I guess it's somewhere else. Maybe not here. Probably I didn't. Doesn't really matter. So we have Hopf algebras here. We have Lie algebras. So a Lie algebra is just a pair of a right module of a module of a Lie algebra, which maps back to this Lie algebra, and this is like this is a map of G modules. Now, again, this gives this M the structure of a Leibniz algebra. And this is what Ladei and Pirashvili really set this thing up for, explaining Leibniz algebras in this way. Now, what else? So one interesting thing about these multiplicative graphs is that you can actually produce a Hopf algebra out of a multiplicative graph. Here I say B algebra because this B algebra only becomes a Hopf algebra if you consider group-like graphs. Well, quite similar to groups and monoids. So again, it looks like a very natural construction, but somehow people who study RACs, they never got to it. So this is a usefulness of considering graphs instead of RACs. So we have the vector space spanned by the arrows, the vector space spanned by the vertices, and the map from here to here is just the, well, it's the boundary map. It's the end minus the beginning. And this way, we can define a coproduct. And the coproduct looks like this. It's a tensor, well, if on an arrow, it looks like arrow tensor its end plus its beginning tensor the arrow itself. So this becomes a B algebra. Again, this is not a trivial fact somehow, even though it's very simple. So one reason why it is non-trivial. Okay, so there is an antipode for you. So there is an antipode. We take an arrow minus an arrow and do some funny things with its beginning and its end. I mean, somehow behind this whole thing there is a notion of the opposite graph. But anyway, so here one can ask one question at this point. So why am I talking about graphs really? If behind all these things we have cubical constructions, why not talk about cubical Hopf algebras, for instance? Well, the problem with the cubical sets, or at least it's something that I see as a problem. Well, maybe there is something very simple that I don't see. So suppose we have a pre-cubical set, and let's take its K cubical set, pre-cubical set, together with a multiplication. So the Cartesian product on the level of cubical sets, of pre-cubical sets, people like to write it as a tensor product, just to distinguish it from the categorical product. So we have this map, and suppose we have the chain complex for K. I mean, in each dimension it's generated it's spanned by the corresponding cubes. So we have the nice algebra map. Well, algebra map. I mean, this multiplication gives us a product on the chain complexes. So So this chain complex of the cubes is an algebra, right? But we don't get the coalgebra structure because on precubical sets we don't have the diagonal map. There's a problem, there is no diagonal map. So here we don't have a diagonal map either, but somehow this, well, all these constructions, they can be thought of as some sort of a diagonal approximation. And the miracle is that this diagonal approximation is multiplicative. So this is a curious thing. So this is something that works for graphs, but not for general cubical sets, apparently. Right, so let me just mention where this goes to and before I finish. If we have, well, we have this Hopf algebra, which is the analog of the group algebra. And in the group algebra, in the usual group algebra, we have the augmentation ideal, and we can take the associated graded filtration. And this way we define, well, this way we can define the lower central series. This way we can define the associated Lie algebra. And more or less the same thing works for in the Lodey-Pirashvili category. To a RAC, to a multiplicative, we can associate some other Hopf algebra, which is already going to be graded, unlike the one I mentioned before. And here, this Hopf algebra, the funny thing about this Hopf algebra is that it's not co-commutative. But if we go to the associated graded, it becomes co-commutative, and then there is the Milnor-Moore theorem, which means that it's a universal enveloping algebra of something, and this is what this something is. I mean, we can identify explicitly in terms of the G action on the corresponding augmented RAC, what kind of Hopf algebra this associated graded Hopf algebra is.